All right, lastly, we're going to have Dr. Jeff Roesler, Associate Head for Graduate Affairs and Professor of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, to discuss his project, Smart Construction Work Zone Safety with ADAS and Passive Road Sensing.
Thank you, Calvin. Thank you, everyone. Looking forward to presenting some work. I appreciate the last presentation because it kind of gave me an introduction to why I got into this. I'm a civil engineer, but primarily on the built roadway side, building the road, designing the road, making sure it lasts there. And a problem that we thought about even in the class starting back in 2012 is how do you change the roadway design to interact more with the vehicle? And so I'll talk primarily about construction work zones in the time I have. But I want to first just say, as the last speaker said, there are issues in rural environments and urban environments where vehicles cannot detect lane lines. And that was the original problem I worked on in our CCAT grant starting back in 2016. And it's a serious problem, as the last speaker said, about localizing. And as more of a materials person, we came up with some ideas that would potentially kind of solve this with passive road sensing. And what does that all mean? Well, there's a vehicle there you can see with a sensor bar in the front, and it appears to be something in the middle of the road, and that's really just ferromagnetic materials that a magnetometer on the car can detect. So imagine that being embedded or in an invisible stripe, and then the vehicle can detect that and know locally where it is in between in the lane. And essentially that's a visualization, like you can create a magnetic field or flux that you can measure on your vehicle through the air. And this would work snow, rain, fog, whatever. It doesn't matter, because you can detect magnetic field fluxes pretty easily with a magnetometer. And the nice thing is you can do this with whatever construction materials we're currently using. So that was kind of our initial work that we did. And this little picture there to give you a little better idea that if you embed this near the middle of the road, you'll easily be able to detect within a couple inches where you're always at, not needing really to see the lane lines, although the camera-based systems work pretty well and should continue to work well as a primary way to keep maneuvering between the lane lines. We did do a study on a really slow-moving traffic place up at our lab in University of Illinois. I won't get into that. That's all been published in a student's thesis. But what I really want to talk about is we kind of pivoted a couple years ago from this idea, not because I didn't like it, but it seemed like it was maybe not ready, or maybe it's not going to work out eventually. I don't know. But people want to talk about construction work zones a lot more than they want to talk about lane keeping for whatever reason. So we looked at safety in construction work zones, and about 1,000 people, or a little less than that now, are killed a year in construction work zones. So could we use the same ideas that I was talking about to kind of tell the vehicle or the driver, you're entering a construction work zone, how fast are you going, you need to merge left, you're leaving the construction work zone. So imagine putting a signal on the road that the vehicle reads, kind of like your QR code is read by camera. Then the vehicle can then tell the driver visually or from audio what they need to do, at least as a better way of having them respond. So we know from construction work zones, primarily speed and lane changes are a big factor in the accidents. And recent research, maybe not recent, but at least some of the last 10 years, researchers have shown that in-vehicle messaging has been much more effective in drivers' reaction to construction work zone, both in terms of speed and lane maneuvering. And there's one study here, you can look it up. They've shown this in simulations with in-vehicle messaging, much more effective in getting drivers to slow down quicker and also merge faster and quicker before they get to the end of the tapered zone. Okay, so where did we fit into this space with construction work zone with with this invisible lane marking that I'm going to be calling. We first looked at, well, first of all, here's how it would work. So as you see up here on your right, you can put certain patterns, very simple patterns on the roads with this electromagnetic material that is really invisible to the driver. It doesn't have to have a color. And if you space it a certain way or you orient the lines a certain way, it can mean certain things. And you just have to have your vehicle pick that up or the sensors pick that up to tell the driver what to do. So horizontal lines, I can pick up speed. If I have an orientation that's somewhat diagonal, I can say merge left. Or if I have certain patterns, I can tell them I'm leaving the construction work zone. And so this is kind of a schematic of our first work where we really simply just, if we know the speed, maximum speed of a construction work zone, we know the spacing and the time distances between different markings. And so we can have a simple algorithm to say, okay, you're going too fast or your speed is fine. So that's one option. And the other option, simple option, is just if you orient the lines like I show here, or if you orient them, skew them the other direction, one's merged left, one's merged right, which is a common maneuver in a construction work zone. And we first just did this in the lab, in the basements. We have our magnetometers here on your right. We have two sets, one subtracting from the other one just because of the background magnetic flux just anywhere where you're at. And then we just looked at, okay, how close can these magnetic strips be placed together such that we can detect them, and we just wanted to work on our signal processing of this data so before we actually took it outside. And this is an unmotorized frame, so it just makes it easier to go back and forth and just get some data really quickly. We just used magnetic tape that you can buy initially, not when we did out in the parking lot. And this is our just simple setup for that. And eventually, with the one on the right is the most relevant. Very simple. At these speeds, we didn't really need to have much spacing between the magnetic tapes, and they wouldn't interact. And we could quickly see the signals if we cleaned them well and figure out what the speed is of the moving sensor bar. So this was pretty successful, and it's pretty easy to set up, although we're not necessarily saying magnetic tape's the best option, but magnetic tape actually works pretty well, and it's removable. The previous slides I had showed about lane departures, we're actually embedding this ferromagnetic material in thin little strips, which I think will work fine too, but you may not want to do that. So some type of striping or magnetic tape would work, and some of that's already out there in the market. Well, these were for our lane orientations for merging. They're on the left. I'll show the field ones. They're a little bit more exciting than the lab ones here. So after we did this, we then decided to do this out in a parking lot. We didn't quite put it on a car yet, though we are working on that right now with another professor who has a autonomous vehicle in our group. And so we started, we did a couple things with this. We wanted to actually create one of the questions we always got is, well, what if I don't want the signal and we put it in there permanently? How am I going to turn it off or take it out? That's a valid question. And so we worked a little bit on that piece, and it turns out, and maybe people know this, and I didn't know this till I started looking into it, but there are materials that you can, there are materials that have fairly low Curie temperatures where I can magnetize and demagnetize pretty easily at about 120 Celsius. So by doing that, I can turn it on to be very active in the construction work zone, and when I want to turn it off, I just heat it up, and the magnetization goes away, and it doesn't actually function like I originally said. So it allows pretty easy off and on of the signal, and 120 degrees Celsius works with current paving materials where I don't really, quote, damage them any significantly. So it seemed like a practical solution. So we're using, happens to be chromium dioxide that we're using here. You have to put very little in we're going to use epoxy-based paint, but it's a simple way to just add it in. We did add this in our previous research into concrete and asphalt just to show it could work and that we could magnetize it and demagnetize it. I'm going to skip this because we don't have time. So here's our setup for the parking lot, or our instrumentation setup. First thing was making our epoxy-based programmable markers that we would put in the parking lot so we could detect them. The second piece is our cart, which is simulating our car. We actually used 3-axis magnetometers. We were using single-axis magnetometers before, and this would allow us to get a little bit more information, potentially to get some redundancy in our signals. So we primarily were measuring the vertical flux, magnetic flux, and now we could measure both lateral and forward, backward-looking flux. And so we created basically an epoxy paint, put our chromium dioxide, we heated it up here with the heat lamp above 120 Celsius. Then we apply a permanent magnet and we can turn on the magnetic field. And we created specimens so we could easily move them outside, so we didn't have to do this outside near our lab. And then we had our cart and our data acquisition system that we could then use. And then we needed a really fast grad student. So we had some competitions to see who would get to run the cart and see how fast he could go. And this is the winner, a Pete Edge, so he's getting a PhD since he ran fast. We set it up so we had about 8 different strips so we could have some repeatability and look at some natural orientation or movement that in the cart, because you're not going to be exactly on the line the whole time. And I'll show a little bit of the results here. So here's our first setup where we're just going to measure speed, and this would be the same. We would calculate speed, and then of course this would eventually tell the vehicle to slow down or the driver to slow down. So this is a Pete Edge running here at about 15 kilometers an hour, so that was good. And you can see our epoxy-based programmable marker there. It is raised above the asphalt parking lot, but you could obviously, you don't need to have it above that. That was just so we could make it easy to set out and take in at night. And then we spent a lot of time just processing the signals, trying to figure out what was the best way to quickly process, because we started working on a real vehicle. So obviously the signal, the interesting thing about magnetic flux is the Earth's magnetic field is actually even stronger than the fields we're creating. So you have to kind of subtract out the Earth's magnetic field first. You have to normalize the data, then you have to filter the data, and then we actually ended up having to take the derivative of the data to kind of help to pick out the right signals, because we want to calculate speeds. And merges also are difficult because you're looking at time differences that are really in the hundreds of seconds. So we think we have most of that covered, at least at relatively low speeds. We haven't done this at 70 miles an hour yet, but I'm sure that we can get that worked out. And then the previous slides were for the vertical direction. This is the Z direction. I don't know why my student picked Z being horizontal, but this is forward looking, or the Y direction, which is laterally. And we had, in this setup with the way we were magnetizing, we were able to get vertical and forward looking magnetic fluxes pretty good and pretty repeatable between the two different axes. Y was a little bit more difficult. Some of the signals dropped out. And one note on that is that we've come up with about, this is all measured in Tesla, nanotesla. We think if we have about 250 nanotesla signal, that we can detect that pretty reliably. And we can always, some of these signals are above 1,000 nanotesla. The Earth's magnetic field's at 50 microtesla, so we're at a pretty low signal. We don't need much of this material. So whether we're doing this for lane keeping or for construction work zone monitoring, we're not adding this huge amount of material to the roadway. Well, kind of the summary slides of the data, we were able to, as you can imagine, it's not a really difficult problem to imagine it working, so it worked pretty well to look at different signal sensors on different axes, and get the speed pretty well. So the blue rows are the speed from the signals, and then the GPS speed comes off the cart's camera. And then we also did a one with speed and orientation with our chromium dioxide invisible markers. And the first four would be the speed signals. And again, to your eye, it's a little difficult to tell, but all the sensors cross the horizontal markers at the same time. But the last four will have a little bit of a time offset, and that's how you know you're going to have to merge left once you process these signals. This has been processed. This is a little bit of a zoom in on one of those markers and how we can actually look at the time differences and then calculate speed from that. So you can actually calculate speed from the parallel or the inclined strips, as well as figure out that it's inclined. So this is all in the vertical direction. And as you can expect, even with the orientated strips, we're able to calculate speed and easily detect that it's oriented left, so that you know you have to merge left. Okay, so I'm not trying to keep you from lunch here. Construction work zones are one piece of something we want to be a lot safer. I think lane keeping is another major option in this. In fact, I think I read that 50% of your lane departures lead to fatalities. And a lot of most of your construction work zone, obviously speed and lane maneuvering are major reasons there's crashes. And I think this idea of programmable sensors in the road, having your road do something even passively so that your vehicles know what to do, I think it's something that the road design engineers need to kind of start thinking about, besides just the traditional lane markings, which need to be made better for computer vision reasons. And I think there's a lot more things we can do with in-pavement signatures that the vehicle can read. I just showed two of them here, and I think I have a few minutes for questions. Go ahead.
So it's speed, but also does it detect the lane departure?
Well, I didn't show that part, but we can do that. We've done that. We did that several years before this.
Okay. Well, another question. What do you see as the pros and cons of this versus like just putting up a speed limit sign near the work zone and having the traffic sign recognition system in the car just tell the car that you're going too fast?
Well, yeah, I mean, that's definitely an option, and you would have an in-vehicle message. But I would probably argue that it's cheaper to put this in the road than pay traffic signals or traffic signs. And I would say that's going to be a lot more expensive, just renting signage for all the places you need on a construction work zone. I couldn't give you a number because I haven't calculated, but just seeing bid prices on signage, safety signage, they're a big component of reconstruction projects. We have a Michigan DOT person. Maybe he can tell me I'm wrong or right. Yeah, you can temporarily deploy it.
Thank you.
Nice talk, Jeff. So,
Thank you.
Quick question. This is basically a special paint, as far as I understand, right?
Sure.
How much more expensive is normal paint?
Yeah, I mean, I haven't done, but it's not going to be that much different and expensive.
So
Yeah.
my point is that, why don't we just paint with this? We have to paint the roads anyway,
Yeah,
right?
Right.
If it's, 10% more expensive, maybe MDOT can pick it up, I don't know.
Yeah.
And in the sense that, especially if you're thinking about deployments of like public transportation and buses and so on, those lanes we're gonna instrument anyway,
Yeah.
right?
Yeah.
So this would be an extra help for those vehicles. So
Yeah,
anyway.
I think if someone asked me to do it tomorrow, I 100% would just do it with paint, put it in. It would be the cheapest, fastest, easiest way to implement it. The only thing is with the lane keeping, you have to have the paint, outside the vehicle, and so you'd have to put a invisible paint line down the middle because you have to be over the car.
I think Raj can confirm that basically we always want the lane sensor line anyway, right? So That's what we try to follow. Lane center line, the center line of the lane, right? All our controllers work on that. So
Yeah. So it wouldn't be, I mean, it wouldn't be a problem to paint kind of a clear-coated paint right down the middle of the road.
Right.
Yeah,
Thanks.
thank you.
All right, folks, if you could thank me or join me in thanking all of our presenters this morning for the safety presentations.